We're going to take today and continue our discussion on concavity, which is coming from our second derivative. And when we talk about concavity today, we're going to talk about our rationals and our radical expressions and functions. We've talked about polynomials, so this is going to go right along with that. We're going to add just a little bit to this one, but not too much. So remember, concavity describes the curvature of the graph. If it's greater than 0, then we're going to be concave up. If it's less than 0, it's going to be concave down. We're talking about the second derivative test, recall. To find our concavity, we're going to find that second derivative. We're going to set it equal to 0. We're also going to be interested in where it's undefined. And that's going to be the new part today when we talk about our rationals and our radical expressions, functions. So we've got to make sure that we talk about where it's undefined. And if you think about a rational equation, what makes a rational function undefined? And that's going to be our denominator. So we're going to be looking at that denominator today. All right, and then we're going to determine our test values within the intervals. Then we're going to come up with our test points. And if it's greater than 0, again, it's concave up. Less than 0, it's going to be concave down. So let's go ahead and jump into our examples. Here we're asking you to determine the concavity. And we're not going to focus too much on finding the points of inflection. We'll talk about those at a later date. What really I want to focus in on today is just talking about the concavity of the graph. So the first thing we're going to do is find our first derivative. And first derivative today is going to be a little more complex. We're going to have that quotient rule that we're going to have to use. So we have x plus 1, derivative of the numerator, which is 1, minus x times derivative of the denominator, which is 1, over x plus 1 squared. Cleaning this up, we have x plus 1 times 1, which is going to be our x plus 1. And x times 1 gives us a negative x there. So our x's will cancel. We're left with 1 times x plus 1 squared. Since we don't have a variable in the numerator, I'm going to take this denominator and bring it to the top as a negative exponent in order to be able to find that second derivative fairly easily. If there was a variable there, I would go and leave it there and do another quotient rule. So my derivative here is going to be negative 2, x plus 1 to the negative third, times the derivative of the inside, which is going to be 1. So notice we just had a nice clean chain rule there. So I end up with negative 2 over x plus 1 to the third. Again, to find my possible points of inflection, or my points of interest, we can call them as well, we're going to set the numerator equal to 0 to figure out where this function equals 0. I'm also interested when it's undefined. So I'm going to take that denominator, and I'm going to set that equal to 0 as well. From that numerator, we should see negative 2 equals 0 doesn't make sense to us. So we can go ahead and get rid of that statement. And really all we're interested now in is this x plus 1 to the third equals 0. I don't know why I've got a double equal. I guess it's really equal to it, huh? So we can take the cube root of both sides to get rid of that third power. And we end up with x plus 1 equals 0. Solving for x, we get x equals negative 1. I'm going to go ahead and take my intervals, and I'm going to take them from any of our critical values, from when it was equal to 0, and where we're undefined. So my intervals, in this case, are going to be negative infinity to negative 1, and negative 1 to infinity. I'm going to go up and come up with the test values. I can plug in negative 2 here, and, oh yes, the all-important testing 0. Now I'm looking at the sign of f double prime of x. So I'm going to take this negative 2 and 0 and plug it into my second derivative. Notice again, as I work with my numerator is negative 2. There's no variable there, so that will always be a negative value. So my denominator is going to determine what the sign of this is. So once I take the negative divided by whatever this is, it's going to give me the sign of the second derivative. So if I plug in negative 2, negative 2 plus 1 gives me a negative 1. A negative to the third power is still going to be negative, and a negative divided by a negative gives me a positive. If I plug in 0, I have negative 2 divided by 1. So 0 plus 1 gives me 1. To the third gives me 1. So negative divided by a positive gives me a negative. So I know then that I'm going to be concave up, and we're going to abbreviate that with just a C. As we're working with these, we understand that C is talking about concavity, and we're going to be concaved up. A negative is going to be concave down. And as we get into, again, points of inflection, we're going to understand that a point of inflection is where we change concavity, and it's a point where we change concavity. So we have a possible point of inflection here between these two intervals, which would be x equals -1. Again, we'll talk about points of inflection later, but that's a possible point of inflection. And we'll talk about why it's just a possibility, again, when we talk about points of inflection. Going into our radicals, again, not really interested in the points of inflection. I'm interested in concavity today. So let's go ahead and find our first derivative. Here we can write the original function as a rational exponent to the 1/2. So our first derivative, we have 1/2 times x plus 1 to the -1/2 times 1, derivative of the inside, don't forget that. We can clean this up just a little bit. I'm not going to make that positive exponent just yet. Since we don't have a variable with the 1/2, we can go ahead and go into our second derivative. Whoa. Looking at this negative exponent. So we're going to get our -1/2 times our 1/2 gives us a -1/4. X plus 1 to the -3/2 now. And times again the 1 derivative of the inside. Now we're going to clean this up to -1 over x plus 1 to the 3/2. Again, I'm going to set my numerator equal to 0. And I'm going to set my denominator equal to 0 in order to find any of my critical values, any points of interest from the second derivative. Again, since, or the way we had it in the first example there, -1 equals 0 doesn't make sense to us, so we can get rid of that. So we're only interested in this x plus 1 to the 3/2 equals 0. Go ahead and take the 2/3 root of both sides, and we end up with x plus 1 equals 0, so x equals a -1. Not always going to be -1, just a little side note there, but this happens to be another -1 value. So we're going to go -infinity to -1 and -1 to infinity. Now some of you, and I hope many of you, realize this interval. Something's happening with this -infinity to -1. If we recall the graph of the square root of x plus 1, and if we go back to our parent function, f of x equals radical x, recall the square root of radical x looks like that. So our domain is restricted for this function. So we cannot have anything below 0 with this function because we can't take the square root of a negative value. Same thing's going to happen over here. When we work with a radical, we really want to look at the restrictions on our domain. And if we recall, that can't be negative, just like the square root of x, that x couldn't be negative. X plus 1 cannot give us a negative value either. So we know that x plus 1 has to be greater than or equal to 0, don't we? So we know that x has to be greater than or equal to -1 in order for this to work. So when we're doing a radical, and we're looking at our intervals, we're going to find that there's going to be at least one, if not more, intervals that we're not going to get anything out of, or anything useful out of. And I caution, because we don't necessarily have to realize that now, but as we get into our test values, we're going to see something happening. So if I take my test values of -2, and I take my test value here, 0, and I go ahead and put those into my second derivative, and I look for the sign of that. Again, I'm looking at -1 over this. If I take -2, -2 plus 1 is -1. So I have -1 to the 3/2 power. And remember, that 3/2 power means the square root of -1 to the third. -1 to the third is -1, so I'm taking the square root of -1, which does not exist. So we see the second derivative here. This doesn't exist for us. And that should make sense to us because we see the restriction on that domain, x has to be greater than or equal to -1. So we can't have anything in this interval that's going to work for us. So again, you could realize that from the original graph and knowing that you're working with a radical and we have restrictions, or we're going to see that within our chart as well. So either way works for me. If we plug in 0, I have a negative divided by 0 plus 1, that's going to give us a positive. To the 3/2 is going to be a positive as well. -1 divided by a positive gives me a negative. So we're going to be concave down at that point. So I have one interval of concavity for this problem. All right, I have one last example, and then we'll get you going here. So we have f of x equals the cube root of x. I can write that as x to the 1/3 power. go ahead and find my first derivative. In order to get to that second derivative, we have 1/3 x to the negative 2/3. And our second derivative is going to be negative 2/9 x to the negative 5/3. Again, I'm going to take that to the denominator, make it a positive. So we have negative 2 over 9x to the 5/3. Again, I'm going to take my numerator equal to 0. I'm going to take my denominator equal to 0. So negative 2 equals 0. That doesn't make sense. And it's not necessarily always going to be that our numerator gives us nothing that works. It just seems that these three examples I got, they don't have a variable in the numerator. I'm going to take my denominator equal to 0. I can divide by 9, so I get x to the 5/3 equal to 0. Take the 3/5 root of both sides, so we get x equals 0. So our intervals, so we have negative infinity to 0 and 0 to infinity. Now, those of you that are thinking, hey, we have a restriction on that domain. Well, do we have a restriction? Remember, we're taking the cube root now. We're not taking the square root. So if this was an even index, we would have restrictions on this x. But in this case, since it's an odd index, we don't have restrictions on this domain. So let's go ahead and test, and we'll see that in our test values here as well. Negative infinity to 0, we can plug in negative 1, and 0 to infinity, we can plug in 1. So looking at the second derivative sign, if I plug in negative 1 into here, if I have negative 1 to the 5/3 power, that's really what we're interested in here at this point. Negative 1, if I rewrite this as the third root of negative 1 to the 5th, negative 1 to the 5th is still negative 1, and the third root of negative 1 is negative 1. So we're going to have a negative divided by a negative, which is going to give us a positive. If I plug in 1, a positive number to any exponent is going to be positive. So we get a negative divided by a positive, which is negative. So we're going to be concave up on the interval from negative infinity to 0. And we're going to be concave down on the interval from 0 to infinity. Recall that this is a parent function, the cube root of x. And if you remember, then you don't have to necessarily know this, but just going to give you an idea of what's going to happen here later on. We see this graph, this is the cube root of x. We see that we're concave up from negative infinity to 0, and then we're concave down from 0 to infinity. So that's going to give you an idea of what's happening there as we get later on and what we're going to be experiencing. So that gives you an idea of concavity with our rationals and our radical functions. Good luck and enjoy, and happy finding those derivatives and concavity intervals.